Good evening, everybody. My name is Phil Rogowski. I am the founder and executive director of the Maryland STEM Festival. We just completed our 7th year, and the Maryland STEM Festival has had a great relationship with NASA at Goddard Space Flight Center. Each year, we have done a number of events with their cooperation. We had 3 or 4 this year. One was NASA at the Table, and we had an event meeting astronaut Vantani and on their new laser communication system that they're just launched. So we thought it was only appropriate that since NASA is a major project coming up next week, what's coming up next week from NASA? Who knows? Anything? Well, next week at 7:20 on Wednesday, the 20th, NASA 22nd, NASA will be launching the James Webb Space Telescope, which is the next generation, the next phase in space astronomy, and it's an exciting event. And we thought it'd be appropriate for us to do a program on it. And I think the best way to introduce that program, to introduce the web, is with a little introduction that NASA created. So Dorothy, if you could start the...
This is your telescope, an engineering marvel, an exploration powerhouse. Use it to look back in time and explore the first galaxies that formed after the Big Bang. To peer into atmospheres of planets orbiting the stars. It's your eyepiece to the uncharted, unknown, and unimagined. This is the largest, most complex, and challenging space telescope ever constructed. It will change our understanding of the universe and our place in it. The James Webb Space Telescope. Equipped with the largest primary mirror ever to be flown in space, at 6.5 meters, it's more than 6 times the size of the Hubble Space Telescope primary mirror. Webb's 4 cutting-edge infrared instruments and cameras operate at super cold temperatures. Temperatures colder than the surface of Pluto. Getting this cold is done with the help of the largest sun shield ever flown, a 5-layer, tennis court-sized sun shield that blocks heat from the sun, Earth, and Moon. Webb will be the first telescope to detect light from the most distant galaxies in the universe. These first galaxies formed about 13.5 billion years ago, only 300 or so million years after the Big Bang. Webb carries advanced technologies to tackle some of the most fundamental questions about the universe. How did the first galaxies form and evolve? Are there chemical signatures of the building blocks of life on other worlds? Is our solar system unique? Launching such a large telescope into space is an incredible engineering challenge. Fully deployed, Webb is too large to fit inside any rocket fairing. Engineers designed it to be folded, like origami, to squeeze inside the European Space Agency's 5-meter diameter Ariane 5 rocket fairing. After launch, controllers on the ground deploy Webb remotely. Deployment is an intricate ballet. For nearly 3 weeks, controllers carefully unfold Webb. After this delicate dance, Webb's golden mirrors are precisely aligned using motors behind each hexagonal mirror segment, adjusting them to form one perfect mirror. Once the instruments are fully cooled, the exploration will begin. Webb is a technological challenge like no other, born of the efforts of thousands of people across the United States, Canada, and Europe. The James Webb Space Telescope is your telescope. Use it to explore, to challenge theories, to see sights yet unseen. It's yours to unfold the beauty and mystery in the universe and our place in it.
As I mentioned, we are very close to Goddard Space Flight Center, and astronomy geeks like us are fortunate to be living in Howard County because not only we're close to Goddard, we're also close to the Space Telescope Science Institute in Baltimore, which I believe you did a little work with.
I did work with.
And we are the home to Johns Hopkins Applied Physics Laboratory, where Dr. May works, which we'll be talking about in a little bit. And we also are very fortunate to have a wonderful astronomy club, the Howard Astronomical League. And the president is here to tell us a little bit about what goes on with HAL and all the things they do and all the other opportunities you'll have throughout the year to enjoy and learn about astronomy. So, from the program, Phil, for a few minutes.
Good evening, everyone. I'm thrilled to be here with all of you. My name is Phil Weichel. I'm the current president of the Howard Astronomical League, HAL. And we're all very fortunate to live in an area that has, even though we have relatively poor skies for observing, but we have a tremendous amount of expertise in astronomy between Johns Hopkins Applied Physics Lab, the NASA locations, Space Telescope, and all the government contractors. And so we're entering into our 22nd year. We're about to have our birthday in a couple of weeks. And we now have over 350 members in Howard County. We're one of the largest astronomy clubs in the Middle Atlantic, and we're one of the most active in the region also. We have an observatory at Alpha Ridge Park in Marysville with a very large refractor there, and it's open to the public for when we have our public events. For those of you who are here in the room, on the table on the way out, we have a little card here that has information on Howard Astronomical League, and it's got our website as well as this business card. For those of you who are streaming this right now, you can go to the website, www.howardastro.org. Just a couple of things that we do. For example, last night we were right here at the library out in front, and we had 7 telescopes out there, and people were looking at the moon, we were looking at Jupiter and Saturn, and we had a nice steady flow of people that were very, very interested in what was going on, and they had a great time. Our membership, I talked about the size, but I want to let everybody know that it ranges from people that are under 10 years old to people that are well over 80 years old. There's people who are amateur astronomers, and there's people who are professionals in the industry, and there's everything in between. It's just a great organization. We have monthly meetings with very excellent speakers like the one we're going to have this evening, and maybe you can speak to Hal one day in the future also. We meet the third Thursday of every month. You can get the specifics on the website, and it's open to everybody. You don't have to be a member to join our public events. If you want to become a member, it's only $30 for the whole family, or $25 for an individual on an annual basis. We've never raised our price in the 22 years. We're all about outreach and education and having a lot of fun. So you can join us at our public star parties where everybody brings their telescopes out, or when we have certain members only events. And we will have solar events throughout the year with solar observing, safe solar observing, as well as all kinds of evening events. And tonight, if you want to get out, take a little look to the northeast later on tonight, you might see the Geminid meteor shower. So once again, Howard Astronomical League, HAL, is honored to be a co-sponsor for tonight's event. And if you want to learn more, come talk to me after the event tonight and pick up the materials on the table. And thank you very much for the time this evening.
As I mentioned, we are very fortunate tonight to have Dr. Erin May from Johns Hopkins Applied Physics Laboratory to speak to us tonight. Dr. May is from Michigan. She went to Michigan State for her undergraduate degree in astrophysics and math. Get that right? Okay. And she received her doctorate from University of Michigan. So we all know who she's pulling for in the Army Corps, right? She has been a postdoctoral researcher at APL since 2019. Her area of specialty is exoplanets, and she has been getting ready for the launch of the Webb and is looking forward to all that data coming in to help expand our knowledge on exoplanets and other areas. So we are very excited, and I turn the program over to Dr. May.
I'm very excited to be here tonight. This is actually the first in-person event that I have done in 2 years. So happy to be here and talk about JWST. I'll give a second for the slides to get up here. So I am an observational astrophysicist. So that means I use some of the biggest telescopes in the world, both in space and on the ground, to study the atmospheres of planets and other stars. Our ultimate goal is to answer the question, are we alone? But unfortunately, we don't currently have telescopes that are powerful enough to actually study terrestrial planets like Earth. We're stuck studying planets that are really big like Jupiter and also really close to their stars, so really hot. But we've been able to use those planets to develop all the techniques that we're going to be using with telescopes like JWST to start looking for habitable planets out in the galaxy. I'm going to spend most of the talk going over some of the really exciting things about JWST, what's going to happen after launch, how it's going to get out to its orbit, and I'm going to tell you a little bit about the work that I'm going to be doing with JWST. Move to the timeline. So I want to start with a brief history of NASA Space Telescopes. And I say brief because I could do a full 30-minute talk on NASA Space Telescopes, and then a couple-hour-long talk on just space telescopes in general from other space agencies. But we started in 1968, which was the first successful NASA Space Telescope, which observed in the ultraviolet. JWST is going to observe in infrared, which is heat, and ultraviolet is how we get burned from the sun. So very different types of light, and it teaches us different things about the universe. But this really started the era of space-based astronomy, and got us to where we are today. After that, the Hubble Space Telescope funding was officially approved in 1978. So back then, scientists had this grand idea to put this really powerful telescope in space that observed a bunch of different types of things to teach us a bunch of different things about the universe. I was recently talking to some of my colleagues, and we were thinking about, back when Hubble was first approved, the people who were planning that, if they had made a list of what they thought the biggest discoveries with Hubble were going to be, absolutely none of those probably ended up being what the biggest discoveries with Hubble ended up being. It was approved in 1978. Move on to the next point. The original launch date was supposed to be 1983, but due to delays with the space shuttle, there were some issues with the launches. They wanted to make sure both the telescope and, importantly, astronauts were safe. It didn't actually make it up into space until 1990. So there's 12 years between the original launch date, or original funding for Hubble before it got up into space, and science changed a ton in that time. So after the launch in 1990, next one, that 7-year delay sounds like a lot, but if we keep moving down the timeline, we're going to see that's actually pretty normal. So move to the next thing on the timeline. So 6 years after the launch of Hubble was when the development for JWST really began. This is when the ideas started getting formulated and scientists got together and figured out, what do we want JWST to look at? And now that we know what we want it to look at, what do we need the instruments to look like? What do we need the telescope to look like in order to accomplish our goals? So this happened pretty quickly after Hubble got into space in 1996. But there was a long gap before the contract was awarded in 2003, and that's when JWST actually started getting built. The original launch was planned for, next one, in 2000, forgot about Kepler. Kepler is completely unrelated to JWST, but I threw it up here because this telescope really changed the face of exoplanet science, which is what I work on. Kepler discovered over 2,000 exoplanets, planets orbiting other stars, and without it, I wouldn't have a job. So I had to put it on the timeline. But if we move on to the next one, the original launch date for JWST was planned in 2010. So they expected it to take originally about 7 years to build. We're all sitting here today because we know it did not take 7 years to build. We are in 2021, the last thing on my timeline, and we are crossing our fingers that JWST is going to be launched before the end of the year. So the current planned launch is next Wednesday at 7:20 a.m. The only delays that are possible at this point are probably just weather. So if it doesn't launch next Wednesday, it's probably the weather, but we should have a launch by the end of the year. So there ended up being a long time since we started thinking about JWST to get here, but we're finally here. We're really excited about the science that it's going to get to do and what it's going to teach us about the universe. So there's a bunch of reasons why JWST is the most absolutely exciting telescope. So first of all, The next slide, it is the largest telescope that we're ever going to put into space. So this is me for scale. This is the mirror of the Hubble Space Telescope. It is about 8 feet in diameter. And this is the 18 mirror segments of JWST to scale, which is about 21 feet in diameter. So nearly 3 times the diameter of Hubble. And what we care about with telescopes is the collecting area, how big the mirror is in total, because the larger the mirror is, the more light it can collect from the universe. You can collect more light, you can look at things that are fainter, and you can look at things that are farther away, and you can also look at them in higher resolution so that our pictures look even prettier and have more science in them, obviously. So making the telescope really big was really important because it lets us study all these unique things that Hubble doesn't let us study. But unfortunately, there is a limit to how big of a thing we can put inside of a rocket and launch it into space. So when JWST was being designed, they had to keep in mind what the largest possible rocket was that could launch something like this into space. So because of that, JWST is going to be launching folded up inside of an Ariane 5 rocket. Move to the next slide. So this is an example of what it's going to look like inside of the Ariane 5 rocket. You can see the nose of the rocket here and Webb folded up sitting right in the top. This launch from the Ariane 5 rocket is provided by the European Space Agency free of cost to NASA, with the condition that European Space Agency scientists get a guaranteed amount of time on the JWST telescope once it's operational in space. I think on the next couple things, I'm going to show you some videos showing how Webb got folded up and put into the rocket over time. So this is showing Webb getting folded up and put into a shipping container, actually, so that it could be shipped on a boat in the ocean to get to the launch site in French Guiana. I'm just going to let you watch it. It's about a minute long. But it's really impressive to me, all of the efforts that went into to get it from California out to French Guiana safely in one piece. So Webb was moved from where it was, it went through the final assembly process and all the final tests completely in secret. Very few people knew actually when it was getting moved, and very few people knew what boat it was getting put on. So none of us knew where it was, other than it's probably on the ocean somewhere right now, until these videos were released when it finally reached the seaport of French Guiana safely. So all of those shots, aerial shots of it getting moved through California to the port, you only knew it happened if you saw it, or somebody told you that it had been moved that night. So you can go to the second video. And this is just Webb getting loaded onto the boat. One of the reasons why it was a complete secret, it first of all cost $10 billion. So we want to not tell people where the $10 billion telescope is if we can avoid it. But also there is a history of pirates holding telescope parts captive on the ocean. There was a telescope being built a few decades ago in Hawaii that had late delivery of the steel for the telescope. I'm not exactly sure why they were late, but they were like 5 weeks late or something with the steel for the telescope. And the captain of the ship refused to hand over the steel because they didn't want to accept all their late delivery payments or late delivery fees. And they threatened to just dump all the steel in the ocean. So because of that and various other reasons of safety, they decided we're not even going to tell anybody where Webb is on the ocean. We're not going to tell them when it's on the ocean, what boat it is. And because of that, and all of the major efforts in getting it there, Webb has safely arrived at its launch port in French Guiana. You can see the boat it's on there. Now that it's there safely, we all know what boat it was, and we could go online and look at the boat trackers and see exactly when it had passed through the Panama Canal and all of that fun stuff. I heard rumors that there were decoy boats as well that, we knew what size boat it needed to be on. So people were speculating that there were all these decoy boats going through the Panama Canal at the same time. So I mentioned it's got a launch folded up because of the size of the rocket. We don't have anything big enough to fit a telescope of this size. So that allows us to launch a really big telescope, this folding up process. But that means when it gets into space, it has to unfold. And that is the scary point, or scary part. There are something like 150 single point failures on the telescope, 150 things that have to go right in the unfolding process for it to be fully operational. And it's going to be doing all of this unfolding while it's flying out to its orbit 1 million miles away from Earth. It's about 5 times further away from Earth than the moon. As it's flying there, the first thing that happens is the arms that hold the sun shield. When this restarts, you see them unfold, and the sun shield itself tensions out. In the video that was shown at the beginning, the sun shield is what pulls the telescope. So the mirrors themselves and the instruments are all on one side, and then the sun shield is protecting them from the heat of the sun. So even though we're out in space where things are freezing, the sun itself is so hot that it would affect our ability to observe with Webb. And we have to block out all of that heat with all these layers of sun shield. I think that is the part I'm most scared about. In some of the original tests when Webb was getting built, these ripped while they were tensioning them. I think everything is well worked out. I don't have any concerns, but I'm also just a little bit terrified about the sun shield tensioning part. But after that happens, the side arms of the telescope unfolds, and then the secondary mirror comes down out front. And I've seen people start calling that the selfie stick of the telescope, so it's kind of what it looks like. Do you have a question?
Oh, why is there a front mirror?
Why is the front mirror? Yeah, so that is the secondary arm, which kind of looks like a selfie stick. What happens is the light comes in and hits the gold mirror part and reflects back to that mirror up in the secondary arms, and then that reflects it back through the middle of the telescope to the instruments at the back of it. There's a video and a few slides that show how that works in a little bit more detail. So while all this is happening, it's traveling to its orbit. If you move to the next slide, I've got a video showing you what this orbit actually looks like. So the sun is at the center, and we see the Earth moving around. And then Webb is out following this orange path out around it. It's at this point in space called L2, which is a gravitationally stable point in space. You can set something there, and it'll just travel around with Earth through space. To scale, here is the Earth compared to where the moon is, compared to where Webb is going to be out in space. You can see that 5 times further away from Earth than the moon is, compared to where Hubble is. So Hubble is orbiting the Earth. It's up around Earth, and it spends half of its time on the day side of the Earth and half of its time on the night side of the Earth. There's a few reasons why it was really useful to put Hubble so close. When Hubble was launched, it went up into space on the space shuttle, and we were able to send space shuttle missions up both to repair it and to upgrade it. And that is why Hubble has now lasted for 31 years, because of these repair and upgrade missions. But because of the fact it spends half of its time on the day side of the Earth, we can't use it half of the time. We can't exactly look at deep space when the sun is blinding the telescope mirrors. So that's part of the reason why we want to put Webb so far away. We can use it all the time, whenever on the day side of the Earth. One of the other reasons is that Webb is looking at a different type of light than Hubble. Webb is looking at heat from the universe, and the Earth itself is actually kind of hot compared to some of the stuff we want to look at. So if we were too close to Earth, the Earth itself would be so bright to the telescope that we wouldn't actually be able to see some of the really cold stuff out in space. Some of the disadvantages of having to put it out this far is we can't go up and service it. So Webb has a very limited lifetime compared to Hubble. Its prime mission is about 5.5 years. So we are guaranteed to, assuming launch goes well and all the unfolding goes well, we are guaranteed to have it for 5.5 years. But it has been fueled for 11 years. So we're expecting to use Webb for the next 11 years. Yeah.
What planet is the blue ring?
The blue ring. So the colors there of the rings don't matter much, but you can see the blue circle that's orbiting around as well. That's Earth.
The big one?
Yeah. I can't jump up and point to my view, but the sun is sitting in the center in the yellow, and the blue circle that's spinning around the sun is the Earth. And then the small little bit spinning around on the orange line is JWST.
I have a question.
Yeah.
Why is the satellite dipping and the circle isn't just horizontal?
Yeah, so it's actually orbiting L2. So it travels in a circle around this point called L2. And that circle takes, I believe, it does 2 orbits around L2 for every year on Earth. So it kind of looks like it's going up and down. And it might be too faint to see up here. There's a little line following JWST's circle orbit around the point L2. You can maybe see it when it comes up in the front.
Thank you.
Yeah. I'm not exactly sure why they decided to do that. I'm sure it's better for some orbital dynamics reasons or whatever for that, because it's going to be spinning around and pointing at different things. Okay, move to the next slide, please. So I mentioned that getting there is a long process because it's got to unfold and it's got to travel there. It takes about a month total after launch before it reaches L2. And during that process, most of the unfolding happens. The first 5.5 days after launch is when the sun shield unfolds. So that's the scariest week for all of the astronomers, is waiting for a confirmation that the sun shield has successfully unfolded in tension and there's been no rips in it. So assuming it launches on the 22nd, we will know by New Year's if that went all okay. And then within the first 2 weeks, all of the mirrors will have unfolded. And that's the other scary part, is making sure all of that unfolding process happens. If anything gets stuck, Webb will be really limited in what it can do. So after 1 month, it'll get out to this point L2 in space. And at that point, things will have cooled down enough on the telescope that we can start turning on the guidance software, all the software that controls the telescope. After about 2 months, the software that controls where it points in the sky turns on. And the components of the telescope that pointed at different points in the sky were actually contributed by Canada, which is a fun fact I just found this week. Also, after those 2 months is when the first instrument is going to start turning on, and we'll get the first pictures from Webb. At that point, they won't be very pretty because all of the mirrors are going to be kind of pointing in the wrong direction at that point. But it's just to confirm that light is getting through to the telescope properly. So we can expect sometime in February to get confirmation that Webb is operating as we expect at that point. And then 3 months after launch, I will align all of the mirrors, and I'll show you that process on the next slide, and start taking the first science quality images. So we're expecting sometime in April or so to get some of the first really pretty pictures from Webb back. Move to the next slide, please. So this is what I mean by all of the aligning of the mirrors. So some of you may have heard the story about when Hubble launched. Its mirror wasn't made correctly, essentially. It needed glasses. So when we were using it to look out at deep space, things were a little bit blurry. And that was one of the great things about having the shuttle at the time, was that we could send astronauts up to fix it. So one of the great things about Webb is we don't have to worry about it needing glasses, because it's made of these 18 independent mirrors. Each of the mirrors can move by themselves, and what we'll be able to do is move each one at a time until we know all of the light is making it down through into the instruments the right way, and all of the images are clear and nothing is blurry. This is a fun little Lego version of JWST that has been fully funded now on Lego Ideas, so we're hoping it turns into a real Lego set, because each of the little mirrors on the Lego version of JWST also wiggle around as well. This is what happens at 3 months, and after this goes through properly, we will be able to start using Webb for science. It'll take about 6 months for all of the commissioning stuff to happen, so just testing every little thing possible and making sure everything is working perfectly. So in about June of next year, people who have gotten time on Webb will start to be able to get their science data down from the telescope. And that is the point at which our 5.5 years start counting down. So the next slide, please. So before I can start talking about the science, we have to actually launch the telescope. And I just added this slide today because they just released some new pictures today of the process of getting Webb on top of the rocket. So over the weekend, this is Webb folded up here. They lifted it up, I think it was something like 10 stories by a single cable. I'm glad they didn't release this picture until today, now that we know it successfully happened. You can't really tell it from this angle, but there is a single cable holding Webb up, lifting it up through that hole in the ceiling, up into this room over here. So it lifted up and then moved to the side and got put on top of the rocket. So there's some white bit down at the bottom. That's the part that's connecting it to the rocket itself. This all happened on Saturday, and today we got the confirmation that Webb is safely sitting on top of the rocket, ready for launch. It was fueled sometime last week. And they also have put the stickers on the rocket. So now that the stickers are on the rocket, there's no turning back. That rocket has to be used to launch Webb into space. Can't use it for anything else. I think there's also some European Space Agency and NASA stickers, and maybe Canadian Space Agency stickers on it as well. That's one of my favorite things about launches, is all of the stickers on the telescope. So launch is gonna happen in 8 days. Assuming everything goes well, we're gonna have some great science results coming out. So I wanna talk about some of the science that Webb is gonna do. So the next slide, I have the 4 major science themes that JWST is gonna focus on. So this doesn't cover all of the science that JWST is gonna do, because there's no way to categorize all of the science into 4 things. But when Webb was being thought of and designed, this is what the plan was for Webb. So the first one is looking at the first light from the universe. So back after the Big Bang, the universe was really dark and light couldn't travel through space at all. And at some point, this thing called reionization happened, which I haven't thought about since my grad school days. But after that point, stars started to form and galaxies started to form, and that light was able to travel through the universe. Webb is, for a variety of reasons, going to be one of the first telescopes that allows us to see some of these first stars that formed in the universe. Any question?
What is the Big Bang?
The Big Bang. That is a great question. The Big Bang is the event that formed the universe. So it wasn't actually a bang that we could hear. So there's no sound in space. But at some point, this point started expanding rapidly, and all of the gas and galaxies and matter in the universe came out of this single event in the history. I don't think we know exactly what the Big Bang was yet. That's something that Webb is going to help us understand, is how the Big Bang came to be. That's a great question that a lot of astronomers think about every day. What is the Big Bang? Okay, so the next thing that Webb is going to look at is the evolution of galaxies. So galaxies haven't always looked like what they look like today. The Milky Way, the galaxy we live in, has all these beautiful spiral arms. But there's a lot of galaxies that kind of just look like blobs, to be honest. Some people who study galaxies might be offended that I call them blobs. But back in the early universe, there weren't a lot of galaxies that had these spiral arms. And over time, galaxies grow, they collide with other galaxies, stars form and stars die. And so what galaxies look like really change with time. And part of what JWST is going to be able to do is look at some of the earliest galaxies in the universe, as well as galaxies that exist now, and understand how galaxies came to look like what they do today, and what are the processes that make them what they are today. The third thing that Webb is going to look at is the formation of star systems. The stars form when these big balls of gas, essentially in space, nebula of gas, start collapsing in on themselves. That forms the star at the center, and then anything that's left over forms the disk around the star that turns into planets and comets and asteroids, everything in the star system. It's really hard to study the birth of stars because it's covered in all of this dust and these gas and dust nebulas. But Webb will be able to look through the dust and see what these stars look like from birth all the way up to stars and solar systems like the one we live in. The fourth major science theme for JWST is the properties of planetary systems. This is the one that I'm most excited about and the one that I'll be focusing on. And the idea here is that we want to understand why the solar system looks the way it is, and how it's unique and how it's just like all of the other planets out there. So to do that, we will be studying planets themselves and measuring what they're made out of, mostly what's in their atmospheres. So what type of gases are present, and then understanding how the atmosphere makes a habitable planet, and how that habitable planet turns into something that might be inhabited with life. So move to the next slide. So I mentioned infrared light a few times. This is the wavelengths of light, the colors of light that what we'll be observing with. So when we think about light, we generally just think about the stuff that we can see with our eyes. And that's called visible light, this rainbow in the middle. And that's primarily what the Hubble Space Telescope observes with. So Hubble is looking at things that we would be able to see with our eyes if they were brighter and bigger and closer by. But light actually means everything from these things called gamma rays and X-rays that are really energetic. X-rays are the same stuff that they use at the doctor's office to take an X-ray, all the way out to microwaves and radio waves, which are low energies. And right in the middle here, visible, is this thing called infrared. And this is heat. This is what our bodies are radiating, what the Earth is radiating, anything that has some temperature is radiating. And JWST is going to be observing primarily at those infrared wavelengths. Now, on the next slide, the reason that Webb looks so pretty and has these, forgot to go to the slides, never mind. So infrared light is heat, and it allows us to see through the dusty regions in space. So I mentioned that a lot of telescopes can't observe the birth of stars, and this is an example of that. On the left, this is an image taken in visible light, so what we would see with our eyes with an old instrument on the Hubble Space Telescope. And on the right is that same region in space taken with an upgraded Hubble with an instrument that can just start to see in the infrared, so just start to see through the dust. And you can see a ton more stars inside of the dusty regions, and those are baby stars, stars that have just recently formed. So this is an example of how JWST is going to be unveiling the universe. It's going to let us see through all of that dust in space. We don't think of space as dusty, we think of space as being empty, but space is a very dusty place. So in order to observe these, Webb has to be designed very specially. Next slide, please. So all of these gorgeous pictures of Webb being gold, that is a very conscious choice. So the mirrors themselves are made of this metal called beryllium, which, if we click for the animation, is a metal that is very strong, but it's very light, even though it's so strong, and it's also very heat resistant. So even though Webb is over twice the size of Hubble and the mirrors, it actually only weighs half as much as Hubble, because beryllium is so strong and so light, the mirrors themselves are a lot thinner. And then after that beryllium, they're coated in this thin layer of gold. Click for the animation. Gold is really good at reflecting infrared light because of some of the properties of the material. So that is why the mirrors are coated with gold. It means that we can't really use Webb to look at visible light, though. Gold is really bad at reflecting visible light that we see with our eyes. Of course, it can reflect some of it. You can see the NASA logo reflected in Webb there, but it's not very good at it. You lose a lot of light in that process. So the gorgeous pictures, the gold mirrors, are very specially picked in order to look through all of those regions and lights in space. Move to the next slide, please. So I've talked a little bit about all of the pretty pictures that JWST is going to send back, but that is not the only way that JWST is going to be studying the universe. So of course, the pretty pictures are what a lot of people care about and what we like to turn into beautiful images on our walls. And JWST is of course going to be really good at that. This is an example of a galaxy that's really far away, showing the resolution on the image that the Hubble Space Telescope will take compared to what resolution we're going to get with JWST. So this still doesn't, it still looks a little bit blurry, but if you imagine all of the beautiful nebula in space, think about how much prettier they're going to look with JWST images. So I'm really excited to see some of those first images of nebula come down from JWST. But the way that I'm going to be using Webb is spectroscopy, which is the process of taking all of this light that we're getting from these objects in space and splitting them up into all of the colors and make them up. This allows us to look at what an object is made out of. I'll be using this to study exoplanets. So on the next slide, please. So exoplanets is a relatively new field of astronomy. The first exoplanet was discovered in 1995, so not until 5 years after Hubble was launched. And since then, over the past 2.5 decades, we've discovered over 4,000 exoplanets, and it has been rapidly accelerating thanks to telescopes like the Kepler Space Telescope that I mentioned earlier, the TESS Space Telescope that is operational in space right now, and a bunch of other ground-based and space-based missions. We discovered tons of different planets. There are planets that are the size of Jupiter, orbiting their stars in less than 2 days. So they're what we call hot Jupiters, very creatively. And they are thousands of degrees. Very, very hot, very unique and weird places. But we've, of course, also observed and discovered planets that are about the size of Earth in the habitable zones of their stars, so about the right temperature for them to have liquid water and be habitable places. Move to the next slide, please.
So
Yeah.
what's the full definition of exoplanet? Just something that's Earth size, or what's
Sorry, what's
the criteria? How do you define an exoplanet?
an exoplanet? An exoplanet is just any planet-like object orbiting another star. So there's no size definition other than it can't be a star. There are other weird objects that kind of cross the boundaries between planets and stars, but we're specifically talking about anything that is about the size of Jupiter and smaller here. So there's 2 different methods that JWST is going to use to study exoplanets. The first is called direct imaging, and we're actually able to take pictures of the planets orbiting their stars. This is an example taken with a ground-based telescope. The star would have been at the middle, but it's been blocked out from the telescope, so the light doesn't reach the telescope. And when you do that, all of the really faint planets that are orbiting the stars start to be visible. The system actually has 4 planets. There's one pretty close to the star that you can see moving around, and then these 3 other ones further away. And the one farthest from the star is really faint, and you can just barely see it because it's just so cold out there. I think there's another animation on this slide. So when we do this, we can measure how much light is in each of these little points. And that tells us how much light is reflected off of the atmosphere. So just like a mirror reflects light. Atmospheres reflect light because of clouds and things in the atmospheres. And the type of light that gets reflected tells us about those clouds. We can also measure this emitted light, which is the amount of heat that the planet has. And we can look at that heat at different colors of that infrared light to learn about how the planet, what types of molecules are in the atmosphere. So is there water in the atmosphere? Is there CO2 in the atmosphere? And all kinds of other interesting molecules. When we observe these types of planets, we're primarily looking at planets that are really young, because just after they form, they're still really hot. But the method that I'm going to use is on the next slide. Oh, sorry. Young and hot planets, what it's best for. So on the next slide, we're going to talk about something called the transit method. So as a planet orbits its star, sometimes it passes in front of its star. And when it does that, it blocks out light from the star. So that's this dip happening here. See this orange planet spinning around the yellow star. When it crosses in front of its star, it blocks out light, and that tells us there's a planet there. When it does that, some of the light from the star is actually going to also pass through the planet's atmosphere and interact with whatever's in the atmosphere. And we can look at how the light interacts with what's in the planet atmosphere to learn about what has to have been in the atmosphere to cause those interactions. If we click for the animation. So we're learning about the atmosphere of the planet. And on the next one, these are good for planets that are relatively large compared to their stars. So the bigger the planet is, the more light it's going to block out, and the easier it is to measure the amount of light that it's blocking out. We can do a whole lot of things with this method. We can figure out if the planet has an atmosphere. We can figure out what's in the atmosphere. We can figure out how big the planet is and learn about what's temperature of the planet. All of that together helps us learn about if the planet is habitable or not. Right, for the next slide. So one of the major things that JWST is going to do for exoplanets is answer the question about, do they have atmospheres? This is going to be absolutely game-changing because to date, we haven't actually detected an atmosphere on any terrestrial exoplanet. So Earth has an atmosphere. Venus, which is about the same size as Earth, has a really thick atmosphere, very unlike what we have on Earth. And then Mars, which is about half the size of Earth, doesn't have an atmosphere. And we want to understand how 3 different terrestrial planets in the same system ended up having very different fates, and why some of them have atmospheres and why some of them don't. So it's one of the major questions that JWST is going to help us answer. And the primary targets we're going to be using for this is this really interesting system called the TRAPPIST-1 system. So the star in the system is actually about the size of Jupiter, so it's pretty small and pretty cold. So all its planets are much closer to the star than the planets in our solar system. This on the bottom is our solar system. So the star is sitting right here, the sun, and we have Mercury, Venus, Earth, and Mars. Venus, Earth, and Mars were all at some point in their history in the habitable zone. You know, Earth is now, and Mars is kind of just on the edge of it. If we look at the TRAPPIST-1 system, so it's TRAPPIST-1 in the middle, the star, it's about the size of Jupiter, and all of that fits right in here. All 7 of the planets in that system. All 7 of them are about the size of Earth, or a little bit smaller, a little bit bigger, and 2 or 3 of them are in the habitable zone of the star. So that sounds pretty similar to our solar system, except it's all pretty smushed together. So what we want to know is which of those 7 planets have atmospheres, and does that end up looking anything like our solar system? Are the planets closer to the star, more like Venus, and turning more to Mars as you move further out? Is that normal? We have absolutely no idea, and JWST is going to answer that question. Move to next slide, please. So I've talked a lot about looking for habitable planets, and you might have heard about people talking about looking for biosignatures at JWST, actually looking for life. Unfortunately, JWST is not quite sensitive enough to look for biosignatures. We click for the animation. Biosignatures are signs that a planet is inhabited. So actually looking for things in the atmosphere itself that point to habitability. So we know on Earth that we need oxygen, and then we breathe out CO2. So on Earth, if there's the oxygen and CO2 in the atmosphere, that's telling us that Earth is inhabited. So if we can look for signs of that in another planet's atmosphere, that might be signs that that planet has life as well. But this is kind of just about at the limits of what JWST is going to be able to do. We click through, I think there's 2 animations. One more. What we will be looking for are these habitability indicators, looking for planets that are habitable, planets that are the right temperature to have liquid water, so in the habitable zone, and then it should have an atmosphere, because we know that life as we know it needs something to breathe. So that fact that JWST is going to be detecting atmospheres on terrestrial planets for the very first time is a huge step towards finding out which planets are habitable, so that down the road we know exactly what targets we want to look for biosignatures and signs of life. We click through the animation. We can move to the next slide. So the reason that we aren't going to be doing biosignatures with JWST, not for a lack of trying, many of us are still going to try. The analogy I like to use is if you have a 5-pound bag of rice, looking for a biosignature is looking like trying to find a single grain of rice in that bag, but you're not wearing your glasses. So there's a single grain of rice in that bag that's a different color, and you forgot your glasses that day, and you try and look at the palm of your hand and see if that grain of rice is in your hand or not. Because you don't have your glasses on, you can't tell exactly how many grains of rice are in your hand. You can't even tell if you're holding any grains of rice because they don't weigh very much. So it gets very difficult to determine if you found that grain of rice or not. If the grains of rice were bigger, or you had your glasses on, which in this scenario, pretend your glasses is a bigger telescope, it would get a lot easier to find those biosignatures. So unfortunately, because Webb was designed in an era before we knew about exoplanets, there wasn't a whole lot that we could do to make it a telescope that would find biosignatures. There were some changes that were made to the telescope during the design process so we could use it for exoplanets. But we're really at this point going to be using Webb to get a good list of targets for looking for life in the future. I think the next slide is just a reminder about the launch. So I had to update this slide since the last time I gave this talk a month ago, because launch is now on December 22nd, next Wednesday at 7:20 a.m. Everything is fueled. As I said, the rocket is stickered, so there's no turning back now. Sitting on top of the rocket now, at this point, the only delays would be weather related. So if you can be up for 7:20 a.m., I really recommend it. And then just hold your breath for the next 2 weeks, essentially. And that's all I have. So I'm happy to answer any questions you have about Webb.
So when you were referring to the mirrors calibrating themselves, more or less with a point of them, or point solution, are they calibrating themselves towards a specific light level signature, like a certain power level, and then commanding those like gimbal mechanisms to point it in one specific location, or are you using something to command it to stay at one geographically stationary location, or one stationary location in space relative to the actual body of the spacecraft?
Yeah, so I think you're asking two different questions. So I'm going to try to answer what I think you're asking. So when the mirrors are aligning at the beginning, when it's unfolding everything, what happens is we expect there to be some vibrations during launch. So, we could have had the mirrors aligned perfectly before launch, but those things are going to move a little bit. So what should happen, if nothing moves, is each mirror will reflect the light back to the same exact point on the cameras. But if things move a little bit, they're not going to all hit the same point, so the images would be blurry. And each mirror just gets iteratively moved until things look like they're overlapping perfectly. So the teams will be taking images and moving a mirror, taking images, moving a mirror until things are nicely aligned. And I forgot what I thought the other thing you were asking was, the pointing.
Yes.
So when we're looking at different regions in space, the entire telescope, not just the mirrors.
So you're actually going to do like orbital operations to rotate.
Exactly, and that's why there's a limit on the lifetime, is we have to use fuel to move the telescope around, and we can only put so much fuel on the telescope.
On top of orbital maintenance operations.
Yes.
So there's a lot of people vying for time at JWST. Do you already have your time allocated? And in either way, how much time do you have, and how long do you have to wait before you can actually start doing the rest of the
Yeah, so just like with Hubble, time gets allocated every year for about a year. So for the first year operations, we put in proposals last November for that. And then panels of astronomers all got together and met and ranked the proposals. And we had those notifications come out, I think, in around March or April or so. So I'm on a couple teams that have data. I'm also on a team that's getting early release science, so some of the first data that Webb is going to get. And the goal of this early release science is to get data in the hands of the community as quickly as possible so everyone gets a chance to play with it before the cycle 2 observations. I forget how many hours are available in the first year. It's essentially however many hours are a year, minus a little bit for, it's got to spin the telescope around and stuff. But I'm on one of the teams that got one of the largest programs for JWST. And our goal there is to look at a lot of terrestrial planets and see which ones have atmospheres and see if those trends follow what we see in the solar system.
So how is the telescope or the system behind the telescope able to distinguish the signals coming from one planet versus another planet because they're just so far away?
Yeah, so I showed on one of the slides what it looks like when the planet crosses in front of its star. So we can tell which planet is which because each planet will have a very slightly different dip when it crosses in front of its star based off of its size. And then that dip happens at exactly the same time every orbit. So even if there were two planets with the same dip, we would be able to tell the difference because they would be happening at different times from each other. Now in the TRAPPIST-1 system, these overlap all of the time, but they're all very different sizes, and they're all orbiting at very different speeds. So it ends up being annoying, but possible to tell them apart. And for a lot of stars, planets like Earth or Mars are just kind of too small to see any of this.
something in our solar system, like Saturn, takes 29 years to go around. We haven't discovered exoplanets that long that we would find Saturn-sized or Uranus-sized or Neptune-sized planets, which take even longer to go around. How do you address that?
That's a question that plagues the community every day. We haven't found cold planets like Jupiter and Saturn and Neptune and Uranus because we haven't been looking long enough. And you typically need to have crossed that transit event multiple times in order to tell that it's actually a planet and to know the orbital period. So we're really missing a lot of information about what all of these other star systems look like in whole. We've really only begun to, scratch the surface of what the inner solar systems look like in these other systems. We do know from dynamical studies that planet systems that have these hot Jupiters really close to their stars probably don't have as many other planets nearby them because of gravitational effects. They would end up throwing each other out of the system. But that doesn't say anything about planets that might be really far away from their stars. The direct imaging that I showed, those planets are typically many tens of AU away, so those get closer to the orbital periods of Jupiter and Saturn, Uranus, Neptune, but they're typically very hot young planets, so also very different from what we have in our solar system. So it's really there's a lot of missing information that we still have.
And as a follow-up, will you be looking at stars that are roughly the same size and temperature as our sun to find a habitable zone that is close enough that the orbit will only take 1 year or 2 years, or maybe even 5 years?
Yeah, so all of the planets on the teams I'm on are orbiting these small stars called M-dwarfs that are about the size of Jupiter, because the smaller the star is, the easier it is to find small planets, because it's all about the size ratio between the two of them. And also the transit events happen more rapidly. So remember, JWST is only a five-year mission. We typically are going to need about 5 events in order to understand exactly what's in the atmosphere. So if there was a true Earth analog around a sun-like star on a 1-year orbit, we would only have 5 chances to observe it with JWST. And that's pretty hard because you never know. There's these other programs that can, like a supernova can go off and JWST decides that's more important to go observe than we missed the Earth event. And there's just, because of this timeline issue, it's only been 25 years since we discovered the first exoplanet, and only about 10, 11 years since we really launched the Kepler Space Telescope that began detecting a lot of planets. We just haven't had the time to find the Earth-like planets around sun-like stars yet.
Several people ask, why wasn't it launched from Florida? Why was it launched from French Guiana?
It's a great question that I am not an orbital dynamicist, so I do not understand all of the reasons for it, but something about being launched along the equator makes it easier to get it out to this point in space, since it's not going to be orbiting Earth.
You said the mission is 5 years, possibly 11 years. Has there been any planning for the next telescope after the Webb yet?
Yeah, so there's every 10 years the community releases this report called the Decadal on what the community's plans are for the next 10 years. And that just came out last month, I think. And in that there were recommendations for what the community thinks the next priority mission should be. There's also a mission in development from a couple decadals ago called the Nancy Grace Roman Space Telescope, which is not quite a Hubble or Webb successor. It's going to be doing different things, but it's on the same scale as Webb. But the next thing has been recommended to be, there's these 2 mission concepts. One of them is called LUVOIR, which stands for Large Optical Infrared Ultraviolet Telescope, and we're really good at naming things. And then another one called HABEX, that stands for Habitable Exoplanet. And they've kind of been mashed together into what the community wants the next mission to be. So the goal for that mission would be to actually image an Earth-like planet around a sun-like star. So the first step is, of course, finding our targets. which includes findings of like planets around falling stars, and also figuring out which ones have atmospheres. This will probably not launch until the 2050s, 2040s, because it has to be redesigned based off of community recommendations. Funding doesn't exist for it yet, and all those things. And we've seen from history it takes about 20 years or so to go into space.
Some of us are wondering, where did you get your astronomical sweater?
Yeah, so I knit this. Actually,
Oh
this was one of my pandemic projects. Was a sweater.
What sparked or inspired you to become an astronomer?
Gosh, I took a astronomy class in undergrad and decided I liked it. I did grow up kind of in the middle of nowhere in Michigan, so there were really nice valleys to look at all of the time. But I didn't have a telescope growing up or anything. Just kind of, I went to undergrad thinking I was going to major in math, and I still did, but I kind of fell in love with astronomy and outer space.
What happened to the Hubble telescope?
So there are, at this point, no plans for the retirement of Hubble. It is still operational. It's had some snafus in the past year where the computers on board are getting old. They're 30 years old, or at least some parts of it are. Some parts have been replaced. But every time it's had snafus, the team over at Space Telescope and here in Baltimore and at NASA have been able to reboot the whole thing and get it back operational. Hopefully it keeps operating for the entire lifetime of J.D. Whisty, and then some. Hopefully we can get some missions that are capable of going up and servicing it again, because it's a great telescope. We just put some more modern instruments on it. It'll remain great for a long time. Personally, I hope that when it is no longer operational, they can bring it back down for a museum, but I don't know that that'll happen.
I'm a volunteer out at NASA, Ozzy, and we wanted that. We wanted Discovery out, launching and going up.
Yeah, we just need to revamp the shuttle program secretly and go steal Hubble when it's no longer operational.
Well, I'd like to thank Dr. May for joining us tonight for this very enlightening discussion. I'm sure everybody learned quite a bit, and I'd like to hopefully have you back after you started getting some of that data, and you can talk about it. If you haven't checked out NASA's website on the web, it's a really cool website, and it has a lot of information. You can even sign up to be a virtual guest for the launch next week, which I have done. So, and of course, you can also just watch it on the NASA channel, but interesting to see what they do for virtual guests. So thank you very much for joining us. We really appreciate it. And where will you be watching the launch next week? At work?
At home.
Okay.
I will not be at work quite at 9 a.m.
Okay.
So we're talking about having a Zoom call, but we'll see.
Okay. Well, of course, we're all praying that it goes off well and that it unfolds and that we'll be getting on every day. Again, thank you very much. So thank you all very much for coming here. Again, check out this website and also check out our website, www.marylandstemfestival.org. We, of course, focus on our big festival in the fall, but we do events throughout the year, and maybe we'll be partnering more with Hal again. And certainly, again, if you aren't familiar with Hal, check them out. Their star parties are wonderful. They're great, and so are their other activities. So again, thank you very much for coming, and please help yourself to a STEM Festival hat or shirt. We've got plenty of them, and everybody have a happy holiday.
Thank you, Dr. May.
Thank you.
Thank you so much.